Welcome to the Day in History for May 20th. Today we're going to talk about cosmic background radiation. Yes, I know, pretty big mouthful, but it's this picture right up here. And you might have seen this picture before. I've seen it a few times. It's an interesting concept. I watched a few videos on it. Some videos you watch and you just leave the video being really confused because it's actually a very complicated idea, but I'm going to try and simplify it so you guys can understand it. It's kind of like when I tried to explain space-time, Einstein, stuff like that, theory of relativity, all that. We're just going to give it a shot because you know what? As long as you have some idea what cosmic background radiation is, you're way ahead of a lot of other elementary school kids. So here we go. Now, big idea for today is that sometimes you just got to wait for the right tools. Okay, because people had ideas that this radiation, or that there might be something there, but we didn't have any tools to find it. So I will let you guys write this down. And here we go. Now, we are in the universe. That's where we are today. Now, this is one of the Hubble Deep Field views. I think I've showed you this picture before, or one like it. But we're really talking about everything. Like, seriously, the universe. Every single thing ever known to exist, that has existed, or will exist, and does exist, is in the universe. And that's what we're talking about today. So, now, the Big Bang. We've talked about this. The great story is about this. Nothingness, tiny, something, everything, okay? I'm not going to go into a whole lot of detail about this because I could probably talk about it for an hour. We could probably spend an entire day talking about the Big Bang. But what I need you guys to understand is that it started tiny and it's been expanding ever since, okay? So it started out tiny, hot, expanded until we are today. 13.77 billion years, about what they're thinking. You know, when you have numbers that big, we're going to be close enough, right? But I need you guys to understand, or to think about the Big Bang as something that started small, changed over time, and got to the point where we're at now. Now, let's keep going. What? Why, Mr. Copeland, would you put a orange slide up with nothing but orange? Well, here's why. Because right after the Big Bang, a few 100,000 years after it, this is what the universe was. It was orange. That's all it was. Because it was so hot. It was so hot that atoms couldn't form, electrons and neutrons weren't bonding like that. It was this giant plasma ball, is what they call it. And it was orange. And that's the color of everything, was orange. Pretty crazy, huh? Now, they say it was about the temperature of the surface of the sun, or even hotter than that. And the sun is orange. Imagine that, huh? Now, as we move on, I want you to take a look at this, okay? This is a wavelength. And what this wavelength is doing is starting close together and then stretching out. And over time, that's pretty much what has happened to the universe. When the universe first formed, it was super hot, super big, plasma. It was pretty crazy, right? Those wavelengths were really close together. But as time went on, they started to spread out. They started to cool off, and the wavelengths spread out, just like this wavelength here, okay? Now, different wavelengths represent different types of light or energy. Now, at the very end, we are going to see gamma rays and X-rays, and those are really fast rays. Ultraviolet comes in there, and then do you see this visible light down here? The light that we can actually see, the colors you see on your computer looking at me right now, represent a tiny amount of the amount of energy that we can see. Now, what we're talking about today are these radio waves towards the end, these infrared microwave rays. Now, this in and of itself, what we're looking at, is a huge topic to study. So you don't need to understand how all of this works right now. But it is pretty interesting how there's these different levels of energy, and we can only see a tiny sliver. All of the light we can see is in that little sliver. Pretty crazy. Now, Remember how I said the big idea was we just needed the right tools? Well, in the 1950s and 60s, we started to get the right tools, which were these giant radio antennas. Now, these radio telescopes were primarily built for the space race, because once satellites started going up, like Sputnik and all these other ones, we needed to find ways to, well, track where they were and hear what they were saying. And so we built these giant radio telescopes. Think about like a nice light telescope that you look through, right? The bigger the mirror, the more light it collects, the more you can see. Well, for these radio telescopes, the bigger the dish, the more radio waves it can collect and the more information you can get. Now, what they ended up seeing was cosmic radiation. This is the end picture they got. Now, they didn't get this picture to begin with, but I wanted you to see what we're talking about today. This is the cosmic background radiation. This is the entire sky, and this is this radiation that's still there. The sky is not empty. Space is not empty. There's this leftover radiation from the Big Bang. Now, Mr. Coughlin, why would you put a TV with static up there? Well, luckily I'll answer that question. And I just learned this today, and it's crazy. Now, a long time ago, before Netflix and before all of these different ways to stream video, you had to actually get TV through an antenna. You had to turn the channel, you had these wires that would come up, you have like an antenna on the top of your house, and you would actually get TV stations into your TV. And sometimes, if your antenna wasn't right or something was blocking it, you would get static. Or if you went to a channel that didn't have a TV program on, you would get static. Now, about 1% of that static is actually your TV antenna picking up the background radiation from the Big Bang. I want you to think about that. If you've ever seen static on a TV, a very small portion of that is actually the energy waves, microwave energy waves from the formation of everything that we know. That is really crazy to think about. That this random sizzling you see on your TV is actually partially a tiny amount from the beginning of the universe. Isn't that crazy? I find that absolutely fascinating. Now, we got to talk about some pretty smart people here. Back in the 1940s, there was a guy, Robert Herman and Ralph Alpher, who had a theory that there had to be some leftover energy from the formation of the universe. Like, there's got to be something we can measure. But we didn't have the tools at the time to do it. Now, these two gentlemen from Princeton in the 60s, Robert Dicke and Jim Peebles, they were theoretical physicists, and they had this idea that there's got to be something left. Like, there's all this energy, we have to be able to measure it somehow. But they didn't have the tools to do it. And so they wrote theories, they wrote hypotheses, they wrote ideas about what might be there, but they didn't have a way to measure it. Now, bring on Arno Penzias and Robert Wilson. Now, these are the two guys that are credited with discovering cosmic background radiation, though without those other four people I just showed you and a whole host of other scientists, these guys wouldn't have got the credit, or they wouldn't have got it. But they get the credit for discovering it because they used the tool to do it. And here's what they used. They used a giant radio telescope. Now, this doesn't look like the normal, like the telescope or the radio dish I showed you earlier, but it works in the same way. It collects radio waves and allows them to see what's happening. Now, these two gentlemen were communication engineers and physicists, and they decided to test this telescope or this radio antenna just to make sure it worked. And so they said, well, hey, let's do a test. Let's point it at an empty part of the sky so that we can get a clean picture so that we know that everything's working right. And so they found an empty part of the sky, okay? They said, hey, look, there's nothing here. We shouldn't see anything. But they did. they saw this background radiation. They didn't know it was the cosmic background radiation, but they saw something and they thought their machine was broken. And so they started checking everything. They started checking, like, why are we getting all this like static? Why are we getting these readings from our telescope if there's nothing there? Because obviously we're pointing it at nothing, but there's something. And they tried everything. They even scared away all the pigeons because they thought that the pigeon poop that was all over the telescope was causing problems with their radio signal. Yeah, they actually went out and cleaned all the pigeon poop off and scared away the birds because they thought their machine was broken. It wasn't broken. It was working just fine. They had discovered the cosmic background radiation. Now, these guys went to this conference, like a physicist conference, and they said, hey, guys, we found this stuff. And then from there, everyone was like, what? And then they met with those guys from Princeton, and they both published papers. And eventually, they got to the point where we now know that there's this background radiation that's still out there from the formation of the universe. Some Nobel Peace Prize for Physics were awarded to some of these guys. It was a huge, huge thing. And we know a lot more about our universe because of it. Now, there is a lot of cool stuff happening with the discovery of deep space phenomena, the universe, all these things. We're really starting to explore and learn more about our universe. And I'm actually super excited to see what happens in my lifetime and yours. Hey, maybe one of you guys will discover something big about the universe. See you guys.